In geometry, an angle is the figure formed by two rays or line segments, called the sides of the angle, sharing a common endpoint, called the vertex of the angle. Angles are usually presumed to be in a Euclidean plane or in the Euclidean space, but are also defined in non-Euclidean geometries. In particular, in spherical geometry, the spherical angles are defined, using arcs of great circles instead of rays. Angle is also used to designate the measure of an angle or of a rotation. This measure is the ratio of the length of a circular arc to its radius. In the case of a geometric angle, the arc is centered at the vertex and delimited by the sides. In the case of a rotation, the arc is centered at the center of the rotation and delimited by any other point and its image by the rotation. The word angle comes from the Latin word angulus, meaning a corner. The word angulus is a diminutive, of which the primitive form, angus, does not occur in Latin. Cognate words are the Greek €1/4 I cubed III, meaning crooked, curved, and the English word ankle. Both are connected with the Proto-Indo-European root enk, meaning to bend, or bow. Euclid defines a plane angle as the inclination to each other, in a plane, of two lines which meet each other, and do not lie straight with respect to each other. According to Proclus, an angle must be either a quality or a quantity, or a relationship. The first concept was used by Eudemus, who regarded an angle as a deviation from a straight line. The second by Carpus of Antioch, who regarded it as the interval or space between the intersecting lines. Euclid adopted the third concept, although his definitions of right, acute, and obtuse angles are certainly quantitative. Identifying angles, in mathematical expressions, it is common to use Greek letters to serve as variables standing for the size of some angle. Lowercase Roman letters are also used. See the figures in this article for examples. In geometric figures, angles may also be identified by the labels attached to the 3 points that define them. For example, the angle at vertex A enclosed by the rays AB and AC is denoted a BAC, or sometimes, where there is no risk of confusion, the angle may be referred to simply by its vertex. Potentially, an angle denoted, say, a BAC might refer to any of 4 angles: the clockwise angle from B to C, the anti-clockwise angle from B to C, the clockwise angle from C to B, or the anti-clockwise angle from C to B, where the direction in which the angle is measured determines its sign. However, in many geometrical situations it is obvious from context that the positive angle less than or equal to 180 degrees is meant, and no ambiguity arises. Otherwise, a convention may be adopted so that a BAC always refers to the anti-clockwise angle from B to C, and a CAB to the anti-clockwise angle from C to B. Types of angles. Individual angles. Angles smaller than a right angle are called acute angles. An angle equal to a 1/4 turn is called a right angle. Two lines that form a right angle are said to be normal, orthogonal, or perpendicular. Angles larger than a right angle and smaller than a straight angle are called obtuse angles. An angle equal to 1/2 turn is called a straight angle. Angles larger than a straight angle but less than 1 turn are called reflex angles. An angle equal to 1 turn is called a full angle, complete angle, or a perigon. Angles that are not right angles or a multiple of a right angle are called oblique angles. The names, intervals, and measured units are shown in a table below. Equivalence angle pairs, angles that have the same measure are said to be equal or congruent. An angle is defined by its measure and is not dependent upon the lengths of the sides of the angle. Two angles which share terminal sides, but differ in size by an integer multiple of a turn, are called coterminal angles. A reference angle is the acute version of any angle determined by repeatedly subtracting or adding straight angle to the results as necessary, until the magnitude of result is an acute angle, a value between 0 and 1/4 turn, 90 a degree, or I/2 radians. For example, an angle of 30 degrees has a reference the angle of 30 degrees, and an angle of 150 degrees also has a reference the angle of 30 degrees. An angle of 750 degrees has a reference the angle of 30 degrees. Intersecting angle pairs. When two straight lines intersect at a point, 4 angles are formed. Pairwise these angles are named according to their location relative to each other. A pair of angles opposite each other, formed by 2 intersecting straight lines that form an X-like shape, are called vertical angles or opposite angles or vertically opposite angles. They are abbreviated as vert. Up. AS. The equality of vertically opposite angles is called the vertical angle theorem. Eudemus of Rhodes attributed the proof to Thales of Miletus. The proposition showed that since both of a pair of vertical angles is supplementary to both of the adjacent angles, the vertical angles are equal in measure. According to a historical note, when Thales visited Egypt, he observed that whenever the Egyptians drew 2 intersecting lines, they would measure the vertical angles to make sure that they were equal. Thales concluded that one could prove that all vertical angles are equal if one accepted some general notions such as, all straight angles are equal, equals added to equals are equal, and equals subtracted from equals are equal. In the figure, assume the measure of angle equals x. When 2 adjacent angles form a straight line, they are supplementary. Therefore, the measure of angle C equals 180 ax. Similarly, the measure of angle D equals 180 ax. Both angle C and angle D have measures equal to 180 ax and are congruent. Since angle B is supplementary to both angles C and D, either of these angle measures may be used to determine the measure of angle B using the measure of either angle C or angle D. We find the measure of angle B equals 180 equals 180 or 180 plus x equals x. Therefore, both angle A and angle B have measures equal to x and are equal in measure. Adjacent angles, often abbreviated as ADJ. AS, are angles that share a common vertex and edge but do not share any interior points. In other words, they are angles that are side by side, or adjacent, sharing an arm. Adjacent angles which sum to a right angle, straight angle or full angle are special and are respectively called complementary, supplementary and explementary angles. A transversal is a line that intersects a pair of lines and is associated with alternate angles, corresponding angle, interior angles, and exterior angles. Combine angle pairs. There are 3 special angle pairs which involves the summation of angles. Complementary angles are angle pairs whose measures sum to one right angle. If the 2 complementary angles are adjacent, their non-shared sides form a right angle. In Euclidean geometry, the 2 acute angles in a right triangle are complementary, because the sum of internal angles of a triangle is 180 degrees, and the right angle itself accounts for 90 degrees. The adjective complementary is from Latin complementum, associated with the verb complere, to fill up. An acute angle is filled up by its complement to form a right angle. The difference between an angle and a right angle is termed the complement of the angle. If angles A and B are complementary, the following relationships hold. The tangent of an angle equals the cotangent of its complement and its secant equals the cosecant of its complement. The prefix co in the names of some trigonometric ratios refers to the word complementary. 2 angles that sum to a straight angle are called supplementary angles. If the 2 supplementary angles are adjacent, their non-shared sides form a straight line. However, supplementary angles do not have to be on the same line, and can be separated in space. For example, adjacent angles of a parallelogram are supplementary, and opposite angles of a cyclic quadrilateral are supplementary. If a point P is exterior to a circle with center O, and if the tangent lines from P touch the circle at points T and Q, then a TPQ and a TOQ are supplementary. The sines of supplementary angles are equal. Their cosines and tangents are equal in magnitude but have opposite signs. In Euclidean geometry, any sum of 2 angles in a triangle are supplementary to the third, because the sum of internal angles of a triangle is a straight angle. 2 angles that sum to a complete angle are called explementary angles or conjugate angles. The difference between an angle and a complete angle is termed the explement of the angle or conjugate of an angle. Polygon-related angles. An angle that is part of a simple polygon is called an interior angle if it lies on the inside of that simple polygon. A concave simple polygon has at least one interior angle that is a reflex angle. In Euclidean geometry, The measures of the interior angles of a triangle add up to I radians, 180 a degree, or 1/2 turn. The measures of the interior angles of a simple quadrilateral add up to 2 radians, 360 a degree, or 1 turn. In general, the measures of the interior angles of a simple polygon with n sides add up to Na-AA2, AA, AI radians, or Na-AA2, AA, a 180 a degree, right angles, or turn. The supplement of the interior angle is called the exterior angle. It measures the amount of rotation one has to make at this vertex to trace out the polygon. If the corresponding interior angle is a reflex angle, the exterior angle should be considered negative. Even in a non-simple polygon it may be possible to define the exterior angle, but one will have to pick an orientation of the plane to decide the sign of the exterior angle measure. In Euclidean geometry, the sum of the exterior angles of a simple polygon will be one full turn. The exterior angle here could be called a supplementary exterior angle. Because each side of an angle has a supplementary angle, there are 2 exterior angles per vertex. It is commonly used in low-Coterminal geometry when drawing regular polygons. Some authors use the name exterior angle of a simple polygon to simply mean the explement exterior angle of the interior angle. This conflicts with the above usage. Plane-related angles, the angle between 2 planes is called a dihedral angle. It may be defined as the acute angle between 2 lines normal to the planes. The angle between a plane and an intersecting straight line is equal to 90 degrees minus the angle between the intersecting line and the line that goes through the point of intersection and is normal to the plane. Measuring angles, the size of a geometric angle is usually characterized by the magnitude of the smallest rotation that maps one of the rays into the other. Angles that have the same size are said to be equal or congruent or equal in measure. In some contexts, such as identifying a point on a circle or describing the orientation of an object in 2 dimensions relative to a reference orientation, angles that differ by an exact multiple of a full turn are effectively equivalent. In other contexts, such as identifying a point on a spiral curve or describing the cumulative rotation of an object in 2 dimensions relative to a reference orientation, angles that differ by a non-zero multiple of a full turn are not equivalent. In order to measure an angle I, a circular arc centered at the vertex of the angle is drawn, for example with a pair of compasses. The length of the arc S is then divided by the radius of the arc R, and possibly multiplied by a scaling constant K. The value of I thus defined is independent of the size of the circle. If the length of the radius is changed then the arc length changes in the same proportion, so the ratio SR is unaltered. N/2I Units used to represent angles are listed below in descending magnitude order. Of these units, the degree and the radian are by far the most commonly used. Angles expressed in radians are dimensionless for the purposes of dimensional analysis. Most units of angular measurement are defined such that 1 turn is equal to n units, for some whole number n. The 2 exceptions are the radian and the diameter part. Turn, the turn, also cycle, full circle, revolution, and rotation, is complete circular movement or measure with circle or ellipse. A turn is abbreviated I, Sic, Rev, or Rod depending on the application, but in the acronym APM, just R is used. A turn of n units is obtained by setting k equals 1/2I in the formula above. The equivalence of 1 turn is 360 a degree, 2I rad, 400 grad, and 4 right angles. The symbol I can also be used as a mathematical constant to represent 2I radians. Used in this way, allows for radians to be expressed as a fraction of a turn. For example, half a turn is I/2 equals I. Quadrant, the quadrant is 1/4 of a turn, that is a right angle. It is the unit used in Euclid's Elements. 1 quad equals 90 a degree equals I/2 a rad equals 1/4 turn equals 100 a grad. In German the symbol AY has been used to denote a quadrant. Sextant, the sextant is 1/6 of a turn. It was the unit used by the Babylonians, and is especially easy to construct with ruler and compasses. The degree, minute of arc and second of arc are sexagesimal subunits of the Babylonian unit. 1 Babylonian unit equals 60. A degree equals a euro/3 a rad. A per mil 1.0471975551 a rad. Radian. The radian is the angle subtended by an arc of a circle that has the same length as the circle's radius. The case of radian for the formula given earlier, a radian of n equals 2 euro units is obtained by setting k equals 2 euro/2 euro equals 1. 1 turn is 2 euro radians, and 1 radian is 180 euro degrees, or about 57.2958 degrees. The radian is abbreviated rad, though this symbol is often omitted in mathematical texts, where radians are assumed unless specified otherwise. When radians are used, angles are considered as dimensionless. The radian is used in virtually all mathematical work beyond simple practical geometry, due, for example, to the pleasing and natural properties that the trigonometric functions display when their arguments are in radians. The radian is the unit of angular measurement in the SI system. Hour angle, the astronomical hour angle is 1/24 of a turn. Since this system is amenable to measuring objects that cycle once per day, the sexagesimal subunits are called minute of time and second of time. Note that these are distinct from, and 15 times larger than, minutes and seconds of arc. 1 hour equals 15. A degree equals a euro/12. A rad equals 1/6. A quad equals 1/24 turn. A per mil 16.667. A grad. Point, the point, used in navigation, is 1/32 of a turn. 1 a point equals 1/8 of a right angle equals 11.25. A degree equals 12.5. A grad. Each point is subdivided in 4 quarter points so that 1 turn equals 128 quarter points. Hexacontade. The hexacontade is a unit of 6. A degree that Eratosthenes used, so that a whole turn was divided into 60 units. Pecus. The pecus was a Babylonian unit equal to about 2 a degree or 2 or 1/2 a degree. Binary degree. The binary degree, also known as the binary radian, is 1/256 of a turn. The binary degree is used in computing so that an angle can be efficiently represented in a single byte. Other measures of angle used in computing may be based on dividing one whole turn into 2 n-equal parts for other values of n. Degree. The degree, denoted by a small superscript circle, is 1/360th of a turn, so 1 turn is 360 a degree. The case of degrees for the formula given earlier, a degree of n equals 360 a degree units is obtained by setting k equals 360 a degree/2 euro. One advantage of this old sexagesimal subunit is that many angles common in simple geometry are measured as a whole number of degrees. Fractions of a degree may be written in normal decimal notation, but the minute and second sexagesimal subunits of the degree minute second system are also in use, especially for geographical coordinates and in astronomy and ballistics. Diameter part. The diameter part is 1/60th radian. One diameter part is approximately 0.95493 a degree. There are about 376.991 diameter parts per turn. Grad. The grad, also called grade, gradian, or gon, is 1/400th of a turn, so a right angle is 100 grads. It is a decimal subunit of the quadrant. A kilometer was historically defined as a centigrade of arc along a great circle of the Earth, so the kilometer is the decimal analog to the sexagesimal nautical mile. The grad is used mostly in triangulation. Mil. The mil is any of several units that are approximately equal to a milliradian. There are several definitions ranging from 0.05625 to 0.06 degrees, with the milliradian being approximately 0.0572957 degrees. In NATO countries, it is defined as 1/6400th of a circle. Its value is approximately equal to the angle subtended by a width of 1 meter as seen from 1 km away. Minute of arc. The minute of arc is 1/60th of a degree equals 1/21600 turn. It is denoted by a single prime. For example, 3 a degree a 30 a euro squared is equal to 3 a plus a 30/60 degrees, or 3.5 degrees. A mixed format with decimal fractions is also sometimes used, for example 3 a degree a 5.72 a euro squared equals 3 a plus a 5.72/60 degrees. A nautical mile was historically defined as a minute of arc along a great circle of the Earth. Second of arc. The second of arc is 1/60th of a minute of arc and 1/3600th of a degree. It is denoted by a double prime. For example, 3 a degree a 7 a euro squared a 30 a euro cubed is equal to 3 plus 7/60ths plus 33,600ths degrees, or 3.125 a degrees. Positive and negative angles. Although the definition of the measurement of an angle does not support the concept of a negative angle, it is frequently useful to impose a convention that allows positive and negative angular values to represent orientations and/or rotations in opposite directions relative to some reference. In a two-dimensional Cartesian coordinate system, an angle is typically defined by its two sides, with its vertex at the origin. The initial side is on the positive x-axis, while the other side or terminal side is defined by the measure from the initial side in radians, degrees, or turns. With positive angles representing rotations toward the positive y-axis and negative angles representing rotations toward the negative y-axis. When Cartesian coordinates are represented by standard position, defined by the x-axis rightward and the y-axis upward, positive rotations are anticlockwise and negative rotations are clockwise. In many contexts, an angle of AI is effectively equivalent to an angle of one full turn minus I. For example, an orientation represented as AAA 45 a degree is effectively equivalent to an orientation represented as 360 a degree AAA 45 a degree or 315 a degree. However, a rotation of AAA 45 a degree would not be the same as a rotation of 315 a degree. In three-dimensional geometry, clockwise and anticlockwise have no absolute meaning, so the direction of positive and negative angles must be defined relative to some reference, which is typically a vector passing through the angle's vertex and perpendicular to the plane in which the rays of the angle lie. In navigation, bearings are measured relative to north. By convention, viewed from above, bearing angle are positive clockwise, so a bearing of 45 a degree corresponds to a northeast orientation. Negative bearings are not used in navigation, so a northwest orientation corresponds to a bearing of 315 a degree. Alternative ways of measuring the size of an angle. There are several alternatives to measuring the size of an angle by the corresponding angle of rotation. The grade of a slope, or gradient, is equal to the tangent of the angle, or sometimes the sine. Gradients are often expressed as a percentage. For very small values, the grade of a slope is approximately the measure of an angle in radians. In rational geometry, the spread between two lines is defined at the square of sine of the angle between the lines. Since the sine of an angle and the sine of its supplementary angle are the same, any angle of rotation that maps one of the lines into the other leads to the same value of the spread between the lines. Astronomical approximations. Astronomers measure angular separation of objects in degrees from their point of observation. 0.5 a degree is approximately the width of the Sun or Moon. 1 a degree is approximately the width of a little finger at arm's length. 10 a degree is approximately the width of a closed fist at arm's length. 20 a degree is approximately the width of a hand span at arm's length. These measurements clearly depend on the individual subject, and the above should be treated as rough rule of thumb approximations only. Angles between curves. The angle between a line and a curve or between two intersecting curves is defined to be the angle between the tangents at the point of intersection. Various names have been given to particular cases: amphicytic or cissoidal, biconvex, xystroidal or cistroidal, concavo-convex, amphicoelic or angulus lunularis, biconcave. Dot product and generalization. In the Euclidean space, the angle I between two Euclidean vectors u and v is related to their dot product and their lengths by the formula. This formula supplies an easy method to find the angle between two planes from their normal vectors and between skew lines from their vector equations. Inner product. To define angles in an abstract real inner product space, we replace the Euclidean dot product by the inner product, that is. In a complex inner product space, the expression for the cosine above may give non-real values, so it is replaced with, or, more commonly, using the absolute value, with. The latter definition ignores the direction of the vectors and thus describes the angle between one-dimensional subspaces and spanned by the vectors and correspondingly. Angles between subspaces. The definition of the angle between one-dimensional subspaces and given by. In a Hilbert space can be extended to subspaces of any finite dimensions. Given two subspaces with, this leads to a definition of angles called canonical or principal angles between subspaces. Angles in Riemannian geometry. In Riemannian geometry, the metric tensor is used to define the angle between two tangents. Where u and v are tangent vectors and gij are the components of the metric tensor G. Angles in geography and astronomy. In geography, the location of any point on the Earth can be identified using a geographic coordinate system. This system specifies the latitude and longitude of any location in terms of angles subtended at the center of the Earth, using the equator and the Greenwich meridian as references. In astronomy, a given point on the celestial sphere can be identified using any of several astronomical coordinate systems, where the references vary according to the particular system. Astronomers measure the angular separation of two stars by imagining two lines through the center of the Earth, each intersecting one of the stars. The angle between those lines can be measured, and is the angular separation between the two stars. Astronomers also measure the apparent size of objects as an angular diameter. For example, the full moon has an angular diameter of approximately 0.5 a degree, when viewed from Earth. One could say, the moon's diameter subtends an angle of half a degree. The small angle formula can be used to convert such an angular measurement into a distance-size ratio. See also, angle bisector, angular velocity, argument, astrological aspect, central angle, clock angle problem, great circle distance, hyperbolic angle, inscribed angle, irrational angle, protractor, solid angle for a concept of angle in 3 dimensions. Spherical angle, phase angle, notes. References. Sources: Heiberg, Johann Ludwig. Heath, T.L., ed. Euclid. The 13 Books of Euclid's Element 1. Cambridge University Press. Attribution: this article incorporates text from a publication now in the public domain. Chisholm, Hugh, ed. Angle. Encyclopædia Britannica. Cambridge University Press. External links: Angle bisectors in a quadrilateral at Cut the Knot, constructing a triangle from its angle bisectors at Cut the Knot, various angle constructions with compass and straightedge, complementary angles animated demonstration. With interactive applet, supplementary angles animated demonstration. With interactive applet, angle definition pages with interactive applets that are also useful in a classroom setting. Math Open Reference.